Is your 5 Steps to a 5, Chapter 11 and 12, quick screencast review. Again, most of you should have the book at home. The screencast is just my take on it. You really should look on your own. That's why you have the resource. So, even though this is AP Physics C, notice there's a lot of kinematics equations here that do not have calculus in them. Now, they're written on your formula sheet differently. You should think about that. So, for example, I think people are pretty confident in the kinematics. Boy, you can tell that bled through, didn't it? So acceleration would be, we would think of this as dv dt. Instantaneous speed would be dx dt at a given time. Average speed is simply delta x over delta t for an interval. The same way, average acceleration for an interval, instantaneous acceleration, either slope of a velocity time graph or dv dt from an equation. So displacement is the area of a velocity versus time graph. So they'll talk about this a little bit. Again, you this year are welcome to put anything you want on your formula sheet because they're not checking it. So you can put the non-calculus versions of formulas on if you think that would be helpful. So they're talking about a lot of stuff down here. Freefall, useful to know. So by definition, freefall is something where the only force acting on the object is gravitational force. So on Earth, the acceleration would be g, which is 9.8 meters per second squared, which is the same as the gravitational field strength of 9.8 newtons per kilogram. AP is perfectly fine if you use 10, but I'm betting this year everything's going to be in variables, so it would be g. So the key thing is if you have something with an acceleration, say something you think is a projectile or might be in free fall, and acceleration is not g, then that tells you there are other forces acting on it. For example, with significant air resistance, an object that's moving upward would have an acceleration, a magnitude of acceleration of less than g, because you have gravity acting. Oh, pardon me. For an object that's being thrown upward and there's air resistance, you'd have a magnitude of acceleration of greater than g. Why? Because in that particular case, you've got gravitational force acting down, and you would also have the force of air resistance acting down. So this would be like what's called a force addition diagram. Technically on the AP, they don't like that. They would like all the forces shown on the free body diagram itself, but you don't have to draw those this year. So at any rate, you would have two forces downward, so your net force would be greater, and therefore your acceleration would be greater than g. Now, once the object reaches the top of its path, if you have and it starts to fall back down, therefore gravitational force would still be downward, but this force, oops, didn't really mean to do that, this force of the air resistance would be upward, acting against the downward motion of the object. So on its way down, the magnitude of acceleration would be less than g. So it's kind of useful to think about that. Okay. They do a couple practice problems here. Algebra. I almost never use quadratic. Yeah. Oh, you're not going to have to worry about that this year, but again, you can think of, for a projectile, something going up and down. You could think of using half the path or two different parts of the path, and that would allow you to avoid you thinking about a quadratic equation. So now they're getting into the calculus part of it. So that's useful to know. Be careful, because sometimes they'll trick you, where they give you an equation, you might think, oh, I've got to take the derivative of this. Well, if they give you an acceleration equation, you might need to take the antiderivative or the integral, and if you need to do the integral, They might ask you to find the displacement. So they might give you an acceleration equation for something that might have air resistance and ask you to find the displacement um, between certain regions. So in that case, you would have to take an antiderivative to find the velocity equation, and then you have to take the antiderivative of the velocity equation to find the position equation, and then put the position in at, say, 2 different times. So which is evaluating the integral. So at that point, again, hopefully you kind of know how to do that. They might ask you to, this year I don't know, but whether or not graphs are consistent with each other. So this is actually super useful down here, differential equations. Again, I don't, and we did examples of this with Coffee Filter Lab this year. Basically what you would be saying in this particular case is how fast you're going will affect the rate of the change of your speed. Why? Because although gravity is constant acting downward, the air resistance is usually related to how fast you're going at an instant in time. And therefore, your net force is dependent on how fast you're going at any given instant, and therefore your rate of change of velocity depends on that as well. So I don't think they're going to ask you to do math for this, but I think they may ask you to understand this. I think we had this on one of our tests earlier in the year, so I think this is actually pretty useful, and it might be something you would ask me to go over during a Google Hangout session. And then these are problems at the end. Chapter 12 deals with Newton's second law. If you recall Newton's first law, law of inertia, basically says an object will continue in straight line motion unless acted on by an outside force. That's one way that you know that any object in circular motion must have some sort of net force acting on it toward the center. So this is F net equals m times a. Oftentimes I'll put F net equals m total times a because we're really talking about the total mass in a situation. So I'll always put like a little subscript m tot. Now sometimes that can be adjusted because, for example, you may want to have a system or part of a system. So if you have two objects connected, say, by a pulley or a string, you know their acceleration has to be the same. So sometimes to find out about the forces such as tension acting on a rope or string, you may want to think of only part of a system. And that tension could be then treated like an external or net force. But this is really important. So that's Newton's second law. Newton's third law, law of interaction, says that forces always exist in pairs. They're equal magnitude, and they act in opposite directions on two different objects. So for example, right now, I am sitting in a chair. Force of me on the chair is acting downward. Force of chair on me is acting upward. They have to be the same size. They're pointing in opposite directions. So force pairs are the big, interactive force pairs are the big idea behind the third law. They talk about that here. I think this might be something useful to go over. Now, notice it looks like they're copying some of the things they did in chapter 10, which is the free body diagram one. The reason I think this is useful is Newton's second law is the master equation of all physics. A equals F net over m tot. So, actually, this is an interesting example. So, you want to remember that, and it applies really just as much in E&M as it does mechanics, because a lot of times you might be asked to find the acceleration of a charge, like an electron or proton. Well, finding the net force on it's one thing, but you need to know the mass to find the acceleration. So this is an example. If you have an object that is sliding downhill at a constant speed, that means your coefficient of friction is force of friction over normal force. The normal component of force is equal to the normal component of gravity, which is mg cosine theta, and the frictional force would have to be equal to the parallel component of gravity, which is mg sine theta. Notice that cancels out, and what that equals is mg tan theta, because I do not know how to do an angle here. Okay, so something like that. Net for a pulley. Yeah, you're going to probably see pulleys in this test. They like that. They like springs a lot too. So you should remind me to ask some questions about springs. Oh, there's a spring right now. So yeah, if this is something where you're sitting on a table and it's not accelerating at all, then the tension in this would just be 2 kilograms worth or 20 newtons of tension. So if there is an acceleration, this tension will be less because the upward force would be less than the downward force of gravity on this thing. So you sometimes could be asked, like, what's the minimum coefficient of friction here for this not to accelerate? Well, basically that means you'd have 40 newtons, or pardon me, 20 newtons of tension in here. This has 50 newtons of weight, so the normal force is 50 newtons. So the minimum coefficient of friction would be 0.4, 20 over 50. More thoughts? Yeah, they talked about this here also. So that's good. Third law. Again, think about the fact that those forces, those interactive force pairs act on different objects. If you remember the take-home test that I gave you, I think it was November maybe, the first page had that wicked problem from, actually I believe it was from Purdue University, and it dealt with these things sliding across a table and oscillating back and forth on a spring. If you save your test, you might want to go back and look at that one. So I think that would be useful. And again, some sample questions. And there should be answers at the end anyhow. Oh, Bert, Ernie, and Oscar. Okay, so that's it.